In section 4.5, what we're going to do is we're going to look at what's called linear approximations and differentials. So linear approximations are just tangent lines. And then we'll talk about differentials later on in this section. So what we're going to use a linear approximation for, which is just a tangent line, is we're going to use it to approximate a function. Calculators are a very recent phenomenon. For hundreds and hundreds of years, we didn't have them. So to approximate functions that are a little bit tricky, such as this curve here, so this represents some function that curves. To approximate the value at that function, let's just say at some point A, what we could use instead is we can use the tangent line at that point, because lines are easier to work with. So what I'm going to do now is I'm going to show you where the linearization comes from, which is just going to be the equation of a tangent line. Okay, so once we figure out the equation of the tangent line, what's really powerful is that we can take any point on our curve that's near this tangent line, and we can put those x values into our linear approximation, and the difference between the two will not be that much. It'll be very close. So the linearization or the linear approximation is a way that we can approximate values for a function when it's really hard for us to work with the function and we don't have a calculator. Okay, so in general, the equation of a line is y minus y sub 1 equal to mx minus x sub 1. So it's really nice to see where this comes from. Well, in this graph, our x sub 1 is the point A, and our y sub 1 corresponds to f of A. So I'm going to replace y sub 1 with f of A, and I'm going to replace x sub 1 with A. Now remember what the tangent line is, right? Its slope is the derivative, which means I can replace this slope with the derivative at that point A. So this is going to be f prime of A instead of m. Now I want to get the y by itself, so I'm going to add f of A to both sides to get y equal to f of A plus f prime of A times x minus A. Remember, this was just the equation of some line. I'm going to replace y with the linearization notation L of x. So L of x, this linear approximation or linearization, is equal to f of A plus f prime of A times x minus A for some point A that would be an x value. If you look at the box where we have our definition of a linear approximation, you can see that that's where this formula comes from. L of x is equal to f of A plus f prime of A times x minus A. When you're asked to find a linearization or a linear approximation, that's the equation that you're going to find. In example 1, it says to find the linear approximation to our function f of x equal to the square root of x minus 3 at x equals to 4. And then we're going to use that linear approximation to find f of 4.1 and f of 4.01. Notice that if I just put in 4.1 for x into my function, I get the square root of 1.1, and I really don't know what that is. So instead, I'm going to use my linear approximation to figure out what that is, or what it's near to. So the first thing I need is I need my f of a. This value here, x is equal to 4. That's my a value. So f of a is f of 4. Put that into my function, I get the square root of 1, which is 1. So I need f of a, I need f prime of a. To get f prime of a, I have to first figure out what the derivative is, and then put in 4. So the derivative of the square root of x minus 3 will turn into 1 over 2 times the square root of x minus 3 after you compute that derivative. So we're evaluating this derivative at our a value of 4. So this is going to be 1 over 2 times the square root of 1, which is 1/2. My linearization or linear approximation is going to be equal to f of a, which is 1, plus 1/2, right, the derivative at a, times x minus 4, or x minus a. Now I could go ahead and clean this up. What I do notice is that the values that I'm putting into my function, 4.1 and 4.01, are decimal values. So I'm thinking when I use my linear approximation, it's probably easier to change this to 0.5 x minus 4. And I could get rid of the parentheses, combine like terms, and end up with 0.5x minus 2 plus 1 would give me a minus 1. So it just depends on what I'm asked to find. What I'm asked to find is f of 4.1, which is going to be approximately equal to my linear approximation at 4.1. So I think that I'm actually going to use the first one, the 0.5 parentheses x minus 4. Because notice when I put in 4.1 for x, this just becomes 1 plus 0.5 times 0.1. And that I can do no problem without a calculator. This linear approximation is going to be 1 plus 0.05 or 1.05. So that's what f of 4.1 is approximately equal to. So now that we have our linear approximation, let's just go ahead and find f of 4.01. So that's approximately equal to L of 4.01, which would be equal to 1 plus 0.5 times 0.01. And that will give me 1.005 when I do the math. So what I'm going to do now is I'm actually going to put in my calculator. I want to see how close I got. So by the calculator, if you put in 4.01 for x in that square root function, you're going to get approximately, so this is the square root of 1.01. In my calculator I have 1.00499, and I think I'm going to stop there. So look at how close these are. My linear approximation was 1.005. By calculator, I got 1.00499, which is essentially 1.005. So oftentimes these linear approximations are an easy way to approximate a function without using a calculator. In our last example, we were given the a value. But what if you're not given an a value? Example 2 says to approximate the value of this function when x is equal to 0.8. So what it's saying is, what is f of 0.8? That's what we need to find. Well, I don't want to put in 0.8 and then take it to the 5th power, so I'm going to multiply 0.8 by itself 5 times and then do the rest of this. That's just, it's doable, but it's tedious. So instead, what I want to do is I'm going to choose some a value. And when I choose my a value, it's going to be close to 0.08. So it seems natural to choose a equal to 1. So again, you're choosing a nice value close to the value that you're approximating. Now I need to find my linear approximation, so I'm going to need f of a, which is 1. If I put in 1 into my function, I get 1 minus 4 plus 7, which is 4. I need to find the derivative and then evaluate it at 1. That would be 5x to the 4th minus 4. So the derivative at 1 is 1. My linear approximation is equal to f of a, which is 4, plus the derivative, which is 1, times x minus a, which is 4. Oh, sorry, which is 1. I lied. So if I were to simplify this linear approximation, it ends up being x plus 3. So f of 0.8 is going to be approximately equal to our linear approximation at 0.8, which is equal to 3.8. All right, so that's approximately what f of 0.8 is equal to. Now I'm going to go ahead and put this in my calculator to see how close I actually got. So by calculator, f of 0.8 is, oh, and I don't have to round it, I get an exact 4.12768. So they are close. I have a 3.8 and about 4.1. But maybe I want to get closer. So example 3, we're going to address this issue. Okay? How close can we get? Or how far away do our x values have to be from a for our approximation to still be fairly accurate? Example 3 says find the linear approximation, okay, which means your L of x, to f of x equal to sine of x at x is equal to 0. So that's our a. This one's actually giving us our a. And then we're going to use it to approximate f of 0.1. So notice that if I was just trying to figure out what sine of 0.1 is, that's very difficult. I don't even know how to figure that out. But maybe my linear approximation will give me something close. And then what we're going to do is we're going to use a calculator to figure out the rest of this question. So let's just look at the first sentence. The linear approximation says that we need to find f of a, and we're given an a of 0. So f of 0 is sine of 0, which is equal to 0. And then we have to evaluate the derivative at 0. The derivative of sine of x is cosine of x. When we evaluate that derivative at our a value of 0, we get cosine of 0, which is 1. Our linearization then is L of x equal to f of a, which is 0, plus f prime of a, which is 1, times x minus a, which is 0. Simplifying this, I just get x. So f of 0.1 is approximately equal to L of 0.1, which is just 0.1. So we approximated f of 0.1. And now what we want to do is we want to use a calculator to find all of our x values, so that when we put these x values in our linearization, it's going to be accurate within 0.2. So going back to what an error is, when we talk about the error, what we're talking about is the difference, the absolute value difference between the function and the approximation. What this is asking us to do is to make sure that that error is within 0.2. So it has to be less than 0.2. To get rid of these absolute values, I would just bound this between, going back to algebra, negative 0.2 and positive 0.2. Now I know what my function is. That's just sine of x. So I can replace f of x with sine of x. And I know my linear approximation, that's just x. Okay, so I'm kind of stuck here. I'm supposed to figure out what x values I can use so that I'm within 0.2 from the actual value. What I'm going to do now is I'm going to use my calculator. I'm going to let negative 0.2, and I'm going to use graphing calculator or a graphing device. So maybe I'll call this my y sub 1 in my graphing calculator. The sine of x minus x, I'll call that y sub 2 in my graphing calculator. And then the 0.2, that'll be my y sub 3 in my graphing calculator. So when we graph all of these together, and it's probably best to use the window, it's going to be a really small window. We'll look at x values from negative 2 to positive 2. And then we'll look at y values from negative 1 to positive 1. That should be a nice window so that you can really see what's going on here. So you're going to look at this graph. And, sorry for the messiness. Sine of x minus x, when you look at that graph, it's going to come down. It's going to go to the origin and then keep going down. The line y sub 1 is going to be down here somewhere. And the y sub 3, the 0.2, will be up here. These are horizontal lines. So the x values that we can use so that our approximations are within 0.2 would be all the x values that give us values between these two horizontal lines. And those x values correspond to, when you look at these points on your graph, this would be a 1.08 and negative 1.08 for x values. So what that means is that if we choose x values between negative 1.08 and positive 1.08, and we put those x values inside our linear approximation, then the difference between our approximation and the actual value of the function will be within 0.2 of an error. So I don't know if my math lab wants you to write this as an interval, negative 1.08 to positive 1.08. But that would be the x values that we can put in so that we have a error or accuracy within 0.2. We're going to move away from linear approximations, and we're going to work our way to differentials. Now we're going to be looking at the relationship between delta x and delta y. So I don't know if you recall, that delta x is the change in x, delta y is the change in y. So let's just suppose that we have this differentiable function on some interval containing some point A. When we look at the change in the value of f, so we're talking about the change in the y values. I always do that. So change in the value of f, that's a change of a y value. And we're going to be looking at how the y value changes between points A and A plus delta x. So this is going to be approximately equal to the derivative at A times the delta x, change in x. Because sometimes we don't really want to find the linear approximation. All we want to do is say, okay, my x values changed. How are my y values changing? What we're going to do is we're going to have all this space just to verify that this is true. So let's just say, oops, I keep forgetting to change this. Let's let x equal A plus delta x. So that would be this x value here, A plus delta x. So what I'm going to do is I'm going to isolate the delta x by subtracting A from both sides. And it's always nice when you can verify relationships. So I have x minus A is equal to delta x. So this says the change in these x values is equal to delta x. I'm going to look at the change in the corresponding y values. So instead of x minus A, I'm going to look at f of x minus f of A. So these are changes in the y value. So this would be a delta y. I know that the value of my function will be approximately equal to the linear approximation. And I know that the linear approximation is going to be f of A plus f prime of A times x minus A. So what I'm going to do is I'm going to subtract f of A from both sides to get f of x minus f of A, which is approximately equal to the derivative at A times x minus A. And now we've already seen that f of x minus A, that's delta y, the change in y. That will be approximately equal to f prime of A, and then we know that x minus A is delta x. So this just verifies that property that says you don't have to find that whole linearization. To find a change in y, all you have to do is take the derivative and multiply that by your delta x. That's what we're going to do in example 4. In example 4 it says estimate the change in f of x. Change in f of x is delta y. So we're going to estimate the change in f of x as x changes, that would be our delta x, from 1 to 1.01. So that change, delta x, is going to be the ending x value, 1.01, and we're going to subtract the starting x value, which gives us 0.01. So that would be my change in x. So for this change in x, what we want to do is find the corresponding change in our y values. If we use the relationship between delta x and delta y, we get the change in y will be approximately equal to f prime of A times delta x. Okay, so where's my A? Well, remember, your starting x value is A, and then we're going to this new x value, a plus delta x. So a is 1. My change in y will be approximately equal to the derivative evaluated at 1 times delta x, which is 0.01. Now it's just a matter of finding my derivative, which is simple. Since this is a polynomial, the derivative is going to be equal to 7x to the 6 minus 3. Evaluating that derivative at 1, I have 4. So my change in my y values will be approximately equal to 4 times 0.01, which is 0.04. The last thing we're going to look at is our differentials. And we need to have that conversation of delta x, delta y, change in y, change in x, so that we can talk about our different differentials. But let's just go back to what a derivative is. So f prime of x is equal to dy dx. So what would happen if I take this equation and I multiply both sides by dx? Then I get f prime of x times dx is equal to dy. Now dx and dy is what we call our differentials. What they represent is a very small change. So if delta x is a change in x, dx is a small change in x. If delta y is a change in y, dy is a very small delta y. And it comes from what the derivative actually is. So let's go back to this graph. Okay, so we have this function, f of x. It's this curve, okay, that's going up. Now, if I look at this point P and the point Q, and I look at this secant line that passes through these 2 points, and I compute the slope of the secant line, so the slope of the secant line is actually going to be the change in y over the change in x. So I'm going to use delta y over delta x. All right. So at P, we have an x value that corresponds to a y value of f of x. And at Q, we've gone a distance of delta x, so we're now at x plus delta x. Okay. To go with this Q value, that's going to correspond to a y value of f of x plus delta x. The difference between these x values is this delta x. The difference between the y values is delta y. If we're trying to find the slope of the tangent line at the point P, what we do is we bring this point Q in closer and closer and closer and closer and closer to the point P, so that we're almost touching, but infinitesimally, if that's a word, close. So our tangent line is essentially the slope of this line, tangent at point P, where we have an x value that's just so close to our original x that that distance between x and x plus delta x is so small that instead of using delta x, we use dx to denote a very, very small change in x. And now look at the corresponding change in the y values. These guys are so close, the change in the y values, that instead of calling it a delta y, which is just some generic change, I'm calling it dy. And that's kind of why we use this notation here, which we call differentials. It denotes a very, very small change in x that's going to correspond to a small change in y. In this box below, well, before that, let's go ahead and look at the slope of the slope of the tangent line. So the slope of the tangent line is the derivative, which is just dy dx. Small change in x corresponding to a small change in y. The definition of a differential. So remember, when we're talking about a differential, we're just talking about this dx and dy, that notation. So all it is a small change in x is the differential dx. Its corresponding change in y is the differential dy, which is going to be approximately equal to the derivative times dx. The change in y, if you look at the y values in the diagram, it's f of x plus delta x minus f of x. That change in y then is approximately equal to the differential. So this is just another way for us to approximate changes in our y value. We can use this formula here, that the change in y is approximately equal to the derivative times the change in x, the differential dx, the small change in x. Example 5 says to write the approximate change in f of x. So that would be a delta y. Given that dx is 0.1, and we're going to look at an x value of pi over 4. So notice that there's no a anymore. We're just taking the derivative, we're evaluating it at pi over 4, and we're multiplying it by dx. So our change in y is going to be approximately equal to the derivative times dx. I need the derivative of my function, and here I'm going to have to use the chain rule. It becomes 10 sine x stays the same times the derivative of sine x would be cosine of x. Evaluate that for my x value of pi over 4. And we have 10 times sine of pi over 4 cosine of pi over 4, which is 10 times the square root of 2 over 2 times the square root of 2 over 2. So I think that's going to be 20 over 4, which is 5. Okay, let's put all this together then. The change in y is going to be approximately equal to the derivative evaluated at pi over 4, which is 5, times dx, which is 0.1. And that's just equal to 0.5. So just another way that we could estimate a change in our y values. And then that's it for this section.